So you saw the situation. I pressed that book against the wall and held it in place. I don't know what you're looking at, but you shouldn't be staring at something. Put it away. Is that a phone? Put it on the sink. Put it away, please. Whoever's phone it is, put it face down on the sink. That's a calculator. Yeah. Okay. Better, but still. What are the forces acting on this book? Get the obvious one. So I absolutely know that. Was the book sliding down? Was the book accelerating up? So I know there's an arrow pointing up. I'm not quite sure what force that is, but I know it's the same size. You okay with that? Let's pretend that I was pushing this way. So this is the meter stick. We'll call that the applied force. Was the book sinking into the wall? Was it flying off of the wall? So there has to be a force pointing this way, the same size as the applied force. What force was that? What? Yeah, all a wall is the ground tilted 90 degrees, so the normal force would tilt 90 degrees. Does that give you an idea as to what that upwards force might be?
Friction.
Yes.
That's so cool. Wow.
If that board was made of ice, would I have to push harder or less hard?
Sure.
If that board was made of sandpaper,
Not very hard.
okay? And by the way, it's something you kind of take for granted. You figure this out when you're 3 or 4 years old. But anytime you're carrying something in your hands like this, by squeezing your fingers together, what you're really doing is you're applying 2 applied forces, getting 2 normal forces in opposite directions on your fingers. Friction is pointing up. And in fact, if you relax your fingers, I'm going to relax my fingers, you can't tell, but you're going to suddenly see it just started to slip there. My normal force was no longer big enough. Sorry, my applied force was no longer big enough to create a normal force, which was no longer big enough to make friction big enough to resist gravity. There's that domino chain reaction. It's just a common everyday thing that we do, but the physics behind it is actually surprisingly linked together and complicated, but kind of cool. That's not today's lesson. That's just an aside. Today's title is Many Body Problems. What we mean by that is more than one mass attached by strings. So in these problems, we have several objects connected by strings. Look up, something like this. But we're going to say one important thing. We're not going to let you yank on the rope like this. We actually have a name for that in physics. It is called a jerk. And the physics of a jerk is surprisingly complicated. For those that take calculus next year, it's a 4th derivative equation, and it's very, very challenging to look at. It would be a changing acceleration. So our acceleration is going to be smooth. But here's what I'm going to argue. Both of these are accelerating at the same magnitude, different directions. But if the one in my hand is accelerating horizontally at 2 meters per second squared, this bottom one is accelerating up at 2 meters per second squared. And the reason I can say that is we're not going to let you yank on the rope or jerk on the rope. It's going to be a smooth acceleration. So if we add that as our condition, that our accelerations have to be constant and smooth, which we actually said at the very beginning of the forces unit. You might recall I said we can only look at constant accelerations, changing accelerations, you need calculus. Then we have a very, very simple workaround. Example 1 says this: find the acceleration and find the string tension. You're also about to get my best, worst joke of the year. It's terrible. Brace yourselves. Find the acceleration and find the string tension. Okay. What does this question want me to find? What might this be a good job for? Did they give me a picture? I'm going to label the picture. So I'm going to zoom in just a bit so that those of you in the back can see a little easier, and then I'll zoom out. I tend to start on the left and just work my way this way in the same order that we read. You don't have to, but if you want your labeling to look like my labeling, then start on the left, work your way right. What are the forces acting on this 3 kilogram mass? Get the obvious one.
Gravity.
Okay. Is there more than one mass in this question?
Yeah.
Then I'm going to call this one M1G. I'll use a little subscript of 1. And I'll call the next one M2, and if there's another one, I'll call it M3. Is M1 sinking into the ground like quicksand?
No.
Is it flying like Superman?
No.
So?
Must be normal.
And you know what? I'm going to call it normal force 1 to go with mass number 1. What else? Is there a rope touching mass 1? What do we call the force from a rope?
Tension.
I'm going to draw a little arrow pointing this way. I'll label it with a T for tension.
Not T1.
Hold that. I'm glad you asked, Matt. How come not T1, patience? Is there friction in this question? How do you know? It says mu equals 0. By the way, a bit later we'll add friction, and all that means is you have one more force pointing that way. I can't say it makes the question tougher. It makes it a bit uglier and more typing and longer, but I hesitate to say tougher. Those are the 3 forces that are acting on mass 1. What are the forces acting on the 2 kilogram mass? Get the obvious one.
Gravity.
Is the good? I'll call it M2G. Is M2 sinking into the ground? Is it flying into the air? I'll call it normal force number 2 to go with mass number 2. This 20 coming from off the page, what was the name that we gave to the mystery force coming from off the page a couple of days ago? This is going to be the applied force. And I often hand draw an arrow on there just so that I don't forget it, because if I don't, I might miss it later on. What else? We're missing one. Is there a rope touching?
Oh, there's
Which way is this rope tugging? This is actually a forces come in pairs, Newton's third law situation, which the reason I didn't label one T1 and the other one T2 because they're the same.
Yeah.
Same rope.
Yeah.
And you can try that. Try tugging on a string or a rope. You can't tug on one end harder than the other end. Tension through a rope is always the same.
Yeah.
Okay. What does it want us to find first? You're going to have to do that first. Our strategy is going to be this. If you give me more than one mass, I'll find the acceleration of everything. Then once I have the acceleration, I can go find individual forces by looking at individual masses. You say that again. You're going to hear me repeat that many times. If you want me to find the acceleration of everything, I'll write an equation for everything. If you want me to find an individual force, I'll write an equation for an individual mass. So looking at this, which way do you think this system is going to accelerate? Who's winning?
Applied.
Okay, and so I wrote here, our solution is we treat the system as a single object and write a force equation. Who's winning? What you're really saying is this. We're going to now walk along the rope. Any force pointing to the right is going to be winner plus. Any force pointing to the left is going to be loser minus. Okay, so I'll start here now. Who's winning? F applied. Walk along the rope. The next one I run into is tension. This one. This tension here, winner or loser.
They cancel out. It doesn't matter.
This tension here, winner or loser.
It's a loser.
This tension here, winner or loser.
Winner. Winning.
Do M1G and M2G show up in my equation? Are they along the rope? So no. Equals. What does that equal? Here is the tweak. Instead of winner minus loser equals MA, it's going to be winner minus loser equals, don't write this down, M1 plus M2 times A. Don't write that down. There's a shorter way to write that. This is actually the winner minus loser equation. It's winner minus loser equals the mass of all of them times A. And it's always been that technically. It's just that you were only looking at one mass. So M was M all. But if you want me to actually, what's the force equation? It's winner minus loser equals the mass of all of them times A. I heard Matt notice something, or here's the dumb, this is not the worst joke yet. This is a dumb joke that I do fairly often. I always say something like, oh, I find these questions so relaxing. You know why I find these questions so relaxing? Because every time I do them, I lose a little tension, right?
Oh, good.
That's not the joke. But tension cancels,
But that was good.
okay? What was I trying to find in part A?
Acceleration.
How would I get the A by itself? Alex's theorem, but we'll divide by M all. This one is so easy, I'll bet Parker can even do it in his head. Let's see. We're going to get this, Parker. A equals F applied over M all. Parker, what is F applied? Good. M all is M1 plus M2. How big is M1? How big is M2? What is 20 divided by 5? I can even go to 3 sig figs and make it look more impressive. Okay. So if you give me several masses attached by a string, I'll write force, I'll do free body diagrams for all of them, and then I write an equation along the string. Who's winning, who's losing, equals M all A. So there's the first part. What did B want me to find?
Tension at the rope.
Why can't I use this equation to find tension?
Because it's going to be 0.
There's no tensions there. Are you ready for the worst joke? I can't use this equation because I have a tension deficit disorder.
Ah.
I have a deficit of tensions. I have a tension deficit disorder because isn't that good?
Yeah.
That's so bad. Okay.
You have ADD.
No, it's because tension's canceled. So, Jaden, here's what I said. Ready? To find the acceleration of everything, write an equation for everything. To find an individual force, like tension, write an individual mass equation. So, Jaden, we're just going to look at this 3 kilogram mass. I've scrolled down, but you should still have it on your paper. What were the forces acting on the 3 kilogram mass, Jaden? What was the obvious one? So I had M1G. What else was there? We called that normal force number 1. What else was there? There's the free body diagram just for that mass. And what I'm going to do is I'm going to pretend, Liam, that this mass here doesn't exist. Okay? There. Who's winning? Yes. Who's losing? It's a trick question. So my equation for this would be tension equals, what does winner minus loser always equal? And this time I'm only looking at one mass, M1A. Parker, how big was M1? What was the acceleration that you and I just found? In your head, what is 3 times 4? Holy smokes. Are you doing math in your head? Do you get a little nerdy adrenaline rush? That's what I feel when I do math in my head.
Good job.
You know what would be really cool? It would be really cool if it didn't matter which mass I picked. If I would get the same tension no matter which mass I picked. So just for giggles, let's try doing the second mass, the 2 kilogram mass on the next page. So there we had M2G, normal force 2. We had F applied, tension. And now we're going to pretend that that 3 kilogram mass does not exist. Who's winning? Which way is the 2 kilogram mass accelerating? To the right. Who's winning? Anything pointing to the right. So again, walk along this section of rope, and we have winner minus loser equals M2A. How would I get the tension by itself? Yeah, swappy dance. And I get this. Tension equals F applied minus M2A. What was F applied? Minus, what was mass 2? What was A? It would be cool if that also worked out to 12. Does it? So it doesn't matter which mass you pick to find your individual forces, although I would argue this one gave us an easier equation. Often one will be easier. Pick that one. But doesn't matter. So again, Alex, what's our strategy? If you give me more than one mass, I'll find the acceleration of everything by writing an equation for everything. Tension will typically cancel. Then if you want me to find an individual force, like tension, say, I'll write an individual equation for an individual mass to find an individual force. You hearing the difference in strategies? Or we might have a mass hanging over a cliff like this. If we have a hanging mass and no external force, we need to understand that it's weight that's causing this whole system to accelerate. Yes?
You made that wrong.
No, I stole that. I think. Yeah, I think I stole that one. So you ready? What does example 3 want me to find? Okay. I sort of like example 3, except it's a bit too easy because there's no friction. We're going to build our up and we're going to remove the wheels and have this sliding with friction in a second. But for now, it wants us to find the acceleration, and then it wants me to find the tension. I'm going to find the acceleration of everything by writing an equation for everything, and then I'll find an individual force by writing an individual equation. And I'm going to start from the left and work my way right. That's just so that our numbering looks the same. What are the forces on this 6 kilogram mass? Get the obvious one. Get the obvious one. Is there more than one mass in this question?
Yes.
I'm going to call it M1G. Is the 6 sinking into the ground like quicksand? Is it flying like Superman? I'll call it normal force number 1 to go with mass number 1. Is there a rope? So? Is there friction? I think the wheels are meant to tell us to ignore friction. So, no. If there was, though, Jaden, I'd have one more force pointing that way. What are the forces on the 2.5 kilogram mass? Get the obvious one. Is there more than one mass? I'll call this M2G. Is there a normal force? How do you know there's no normal force? It's not sitting on a surface. Okay. By the way, I think in Physics 12, I give a question where we actually have it sitting like that. And we say, hey, what would the normal force be in this situation? It's calculatable. But what else? Which way? Okay. Which way must this accelerate? Well, if this is like a toy car with no batteries or a cart, and this is hanging over a cliff, I think it has to go that way. There's no way that it can spontaneously just start crawling up the cliff. So I think winner is, once it gets over here, anything pointing down is winner plus. Once it gets over here, anything pointing up is going to be loser minus. You okay with that? So now, part A, it wants the acceleration. Who's winning? Can you actually read what I wrote? M2G. And now I'm going to walk along the rope because that's what's distributing the force. So as I walk along the rope, I want to run into this tension. Now you might say it's pointing up. Isn't that positive? I think we've let down and right be winner. So this tension here, loser negative. Keep walking, keep walking. What about this tension here? What about M1G? Not part of the question. I'm writing an equation along the rope. Is M1G along the rope? Nope. It's a force that's occurring, but it's not affecting this situation, so don't worry about it. What does winner minus loser always equal? Well, do I have forces from more than one mass on the left? Yes, I better have more than one mass on the right. And by M all, I mean M1 plus M2. Not times, plus. Everybody stretch. Everybody, pencils down, stretch. Come on, everyone. These are great. You get to lose a little tension. Isn't that good? Oh. Wow. These questions are like a little spa treatment. Oh, so good. What am I trying to find? How? Alex's theorem. A is going to be M2G divided by M all, or if you want to, you could write M1 plus M2 because that's what M all is. How big is M2 exactly as a number? How big is M2? 2.5? How big is G? All over 6 plus 2.5. Now, give you a little built-in error check. What are we trying to find?
Acceleration.
If we cut the rope, what's the maximum the acceleration could be? 9.8. This object is slowing it down. You're going to get an answer less than 9.8. If you don't, you messed up. So a bit of a built-in error check if you make a typo. Type this into your calculator. What do you get? Is this a fraction? Yep. More than one thing on the top. You get 2.882?
Yeah.
Shouldn't it be negative because we're down? No, we decided to let that way be positive because it made the math easier. Okay? So we're just finding the magnitude of the acceleration, and also because there's two different directions. One is accelerating to the right, one is accelerating down. I'm not going to ask you for the direction. I'll just get the magnitude. We'll figure it out later. So I'm going to write 2.88, but I'm going to store this on my calculator. Okay. What does B want me to find? An individual force. I'll look at an individual mass. Now, I can find the tension from either one of these. So what we're going to do just this once, we're going to do it both ways. And I'll have half of you do it one way and the other half do it another way. But first, let's generate our equations. So if we want to find the tension, first of all, look at the 6 kilogram mass. Which way is it accelerating? Who's winning? No, we're only looking at this. This doesn't even exist. I heard someone say it. What? Who's losing? It's a trick question. What's that going to equal? M1A. So to solve for tension, I would go M1, 6 times my answer button, which has the 2.882352941. Don't type that in just yet. If you did, no biggie. What about on the right? What about this mass? Who's winning? Who's losing? Tension equals M2A. Swappy dance. Here, you'll get tension equals M2G minus M2A. Here, you'll get tension equals 2.5 times 9.8 minus 2.5 times answer button. So everybody on this side, on this half, can you type in the right-hand equation on your calculator? Can you go 2.5 times 9.8 minus 2.5 times answer button? This side, can you go 6 times answer button? And we should get exactly the same decimal. So I'm doing the right-hand version. You guys are trying the left-hand version. Do you all get 17.294111765? Which one of those gave us an easier equation? I would have used the 6, but I don't care that much. It wasn't much more work to use the right-hand one. Okay. Liz, did that work, Liz, or not? Yeah? It's a force. Yes, units required. It's a force. So it's a force. Yeah, question 1 from the quiz, newtons. So tension equals, what was it, 17.3? I'll go to 3 sig fig, 17.3 newtons. I don't take marks off, no. As long as you round off properly. If you went 17.29 and you somehow said, oh no, that 9 should get rounded up to a 0. No, I would not. Okay? Yep. So again, what's our strategy? If you give me more than one mass, find acceleration of everything by writing an equation for everything. Individual forces? Oh, individual masses. We can even handle problems that have friction. I like example 4. I like example 4. I like example 4. Example 4 is a nice question. And you may start to notice a trend, because what does it want me to find, Liam? The acceleration and then the tension. Okay. I'm going to start with a 3.2. What are the forces acting on the 3.2? Get the obvious one. Is there more than one mass? I'll call it M1G. What else?
Normal force.
I'll call it normal force number 1 to go with mass number 1. What else?
There must be friction because there's a
Which way?
to the left.
And I'll call it friction 1 to go with mass 1. That would be in case there was more than one friction, and there will be later on. So, okay. What else?
There's got to be tension.
Yep.
Spencer's right.
Tension is what's applying the force to this. Okay. What are the forces on the 2.8 kilogram mass? I'll call it M2G.
Tension on top.
Anything else?
Tension, something like,
Okay, that's it.
let's use the one on
Okay.
the right.
Well, we can't use that yet. First, what do we have to find?
Acceleration.
We're going to write an equation for everything. Which way is this sliding? Well, there's two possibilities. Friction could be so big that it's actually just hanging and stopped. Okay? That's a pretty small mu, so I doubt it. So I suspect this is accelerating this way. I would find out I was wrong if when I tried to find the acceleration, my answer ended up being what? Then I would panic and say, wrong winner. Go back and look. But for now, I'm not going to try and trick you in grade 11. Physics 12, I would feel comfortable giving you a question where friction was so big that nothing was moving, but I'm not going to pull that off on a test or a quiz here. I might have done one like that in the homework. I can't remember. So,
But if one's heavier than the other, the other one.
yep. Okay, so you ready? Parker asked a great question. He said, if one's heavier than the other, would the other one even move? Yes. Yes. First of all, if there was no friction, this could be 0.1 grams, and there's still technically an unbalanced force. It's going to accelerate slowly, but it's going to accelerate. Okay? As long as, well, let's write our equation, Parker. Who's winning? More specific, that's not a force. Which force in my free body diagram is winning? And please tell me which M? Or M2G, as most of us wrote? And so you've just decided, Parker, that that's winning. And again, we're going to walk along the rope. So walk along the rope. This tension here, winner or loser? The first T?
No.
Loser? Okay. What about the second tension?
What's that equal?
Ooh, what about friction force number 1? Because it's along the rope as well. Winner or loser?
That's a loser. Wow.
What does that equal? M all A. Parker going, why am I stretching? I get to lose a little tension. I like that. Parker, the tug of war, it turns out, is between M2G, look up for a second, and friction. As long as M2G is bigger than friction force, and I should have put a 1 there, friction force number 1, it'll slide. So this can be a bigger mass as long as when you calculate friction, it's less than M2 times 9.8. And in fact, this is the 3.2 is a bigger mass, but you'll find we have picked the right winner. We're going to get a positive acceleration. How would I get the A by itself?
A equals M.
So look up. If you want to save yourself a line of writing, on this line, if you want to, you could cross that out and just do that. And I'll figure out that you did that step then instead of rewriting one more line and ending up there. Yeah. I'm saying negative T plus T is 0. If tension was 17 newtons, negative 17 newtons plus 17 newtons makes no difference. The X. Oh, sorry. Yeah, I'm crossing out this whole thing. So let me do this a little more blatantly. What I'm really saying is that whole thing vanishes. Okay. Now, time to plug in numbers. A equals, what's M2? Oh, wait a minute.
We don't have that yet.
Let's keep going. Yeah, we do. Let's write M2G minus. What should I write instead of friction? Friction is what times what? Mu times, I don't know the normal force. Oh, but look. I know another force the same size as normal force number 1. Which M?
3.25.
M1G. And this is where the M1 will show up. The M1 will show up, M1G will show up in friction, if you're using friction, divided by M1 plus M2. There's my generic equation. Now let's plug in numbers. A equals, how big is M2 exactly as a number? Question told me. 2.8. How big is G?
9.
Not negative. We took care of that with our winner minus loser stick. Minus, what's mu? I don't know. What's mu with you? 0.12.
That's what's
M1.
3.2. Better be.
G.
Must be 9.8.
All over
All over.
3.2 plus 2.8. I would strongly encourage all of you to try typing this in. This is the level of complexity I expect you to be able to handle on your calculator. Is this a fraction? Brackets around the top or fancy schmancy fraction button. Brackets around the bottom or fancy schmancy fraction button. Oh, built-in error check. I know I'm going to get an A less than 9.8 because if I cut the rope, the fastest that 2.8 could accelerate is at 9.8, and it's getting slowed down by friction. Bracket 2.8 times 9.8 minus 0.12 times 3.2 times 9.8. Close off the top. Divided by, open up the bottom. Parker, you want to try this too, right?
I already did.
Oh, you already did? Do y'all get 3.9461 that?
No. I keep getting 10.
Okay, I'll look at yours in a second. Don't clear your calculator. Yeah, I would write 3.95, but I would store this on my calculator because I think we're going to use our answer button to find tension. Matt, let me come look at your calculator. We've come a long way. Look at what we're doing. This is actually a 1, 2, 3, 4-step question that we've reached now, where a month ago when we started doing some of this, that would have terrified a lot of you. But we build up to it. I often put a little box around the acceleration because I know I'm going to use this later, and that's kind of my touchdown, spike the football dance. That's part A. What does part B want me to find? Okay, don't write this down, look up. What would the equation be for mass 1?
So, too difficult. It's not
More specific, though, what would the equation be for mass 1? Don't write this down, but we're going to visualize it. Who's winning on mass 1? On the 3.2, who's winning? Who's losing? So I could find tension by going like this. Or, what would the equation be for mass 2?
T equals MA.
No.
M2A.
Who's winning?
Oh, yeah. What? M2G.
Who's losing?
T equals MA.
M2A. I would probably use this one because finding friction is a bit of a pain. So even though it'd be slightly easier to get the T by itself with that one, write this. I think we're going to use mass 2. I think we're going to say, write this down, winner minus loser equals M2A. Because I've gotten pretty good at the swappy dance. That's not a big step for me anymore. What's right in front of the T that I don't like? The negative. Okay, swappy dance. So tension is going to be M2G minus M2A. How big was M2? 2.8 times 9.8 minus 2.8 times, and I'm going to use my answer button there instead of the 3.95. And I get 16.4.
Yeah.
If you didn't use your answer button, if you used 3.95, you would have gone 2.8 times 9.8 minus 2.8 times 3.95. You're close, but you've done extra typing. Instead of just hitting your answer button, you're having to type 3.95. You might make a typo. You're much less likely to make a typo just hitting one button. So figure out how to use your answer button. It's less work, it's less error, it's more accurate. It's a triple win. It's a force units. Okay, so acceleration, meters per second squared, and then you can find individual forces, newtons. A couple more, we're done. This might be the last one. Yes, it is. Last one. We can even handle more than 2 masses. In fact, honestly, we can handle 10. I'm going to do 1 with 3 so you can see how it scales up. I think in the homework I give you 1 with 3. I'm not going to give you 1 with 3 as a test question, maybe as a bonus, but not as an actual test question. It's so much more writing. It's not harder. It's just, okay, now I got to find this to find this, and I got to find this to find this, then I got to find this to find this. It's more steps. Sorry? There's a couple of questions with 3 masses, but I might change that. We'll see. First of all, any suggestions on how we might want to start?
Let's start from the left.
Okay, free body diagram. Did they give me a picture?
Yes,
Cool.
they do.
Okay.
Make it all nice.
What are the forces on the 1 kilogram mass? Get the obvious one.
You got gravity.
I'm going to call it
M1.
M1G.
And you got tension.
Tension. Wait a minute. Is there more than one mass?
Yeah.
Sorry, is there more than one rope?
No.
Is there more than one rope?
It's all one.
Okay.
And two.
Because it's more than one rope, I'm going to call this, I don't know, how about tension 1? And I'll call the other rope tension 2.
Okay.
Or you could call it tension L for left and tension R for right side rope, or come up with something that works for you, and preferably something that only involves writing one character. Don't write the word left or right, let's abbreviate. There's the forces on mass 1. So what force is causing mass 1 to accelerate? Tension 1. If mass 1 is going up, I think it's probably the loser, because I think the heavier mass is the winner, but we'll find out. What are the forces acting on mass 2? Get the obvious one.
M2G. You got normal.
I'll call it normal force number 2 to go with mass number 2. What else?
You got tension on both sides.
So I'll have tension 1 pointing to the left. I'll have tension 2 pointing to the right.
It's a very tense situation.
What have we missed?
Oh, so much.
Oh, is there a coefficient of friction there? Then there must. Which way would friction be? It depends on which way it's sliding.
Likely to the right.
Probably to the right. If I solved this and I got a negative acceleration, then I would say, it's going to the left. I would have to flip friction around and redo everything. But again, I'd only have to change a few things. So I think to the right, I think friction is pointing to the left. I'll call it friction force number 2 to go with mass number 2. What are the forces acting on mass 3? Get the obvious one.
Gravity. M3D.
And tension 2. Who's winning? I think what's causing this whole thing to accelerate is the force of gravity on the 8 kilogram mass, because it's heavier than the 1 kilogram mass. So I think anything that ends up pointing down and right once it gets there will be winner plus. So let's write our equation for everything. And again, we're walking along the rope. Who's winning? M3G. What's the next force I run into? Tension 2? Is this tension 2 winner or loser? I totally disagree. I just decided down was winning,
Oh, yeah, sorry.
right? Loser. I meant the force. What about this tension 2?
That one's winning for sure.
Then I see tension 1. This tension 1, I think loser. Oh, don't forget friction force number 2, which is also a loser. Keep going, keep going. This tension 1, now you might be tempted to say, since this tension 1 is pointing up and this tension 2 is pointing up, this must be a loser. But if you follow it, I think when it gets to this side, I think it's going to end up pointing down winner plus. Yes?
Yeah. Yeah.
And you might be tempted with this M1G to say, well, it's pointing down. I called that a winner. But if you follow it, when it gets to this side, I think it would actually be pointing up. I think it's a loser.
Oh, I'm so excited.
What does that equal?
That's
M all A.
all
Yeah, this is like a double relaxation spa treatment, because losing tension and losing tension. Oh, what are we trying to find? If you don't mind, I'm going to go and use Alex's theorem on the first line already. Save myself a line of writing. Okay. What shortcuts can I take? Look up. In the middle, friction is what times what? First of all, it's not mu times m. It's mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as a normal force. What? Because this is a lot of writing, I would have no problem, look up, if you did this. And said, hey, Mr. Dewick, that's where I did the substitution. I'm okay with that. On a test, I might write more, but this is how I would do this in my homework, Jade. And this is about my level where I don't try doing this in one step, not writing anything all on my calculator. This is where I got to write stuff out. All right, let's plug and chug. We're going to get A equals, what's M3? 8? 9.8 minus, what's mu? I don't know what's mu with, what was mu? 0.25 times M2, 9 times 9.8. Minus 1 times 9.8, all divided by 1 plus 9 plus 8. Is this a fraction?
Yeah.
Brackets around the top and brackets around the bottom. This is about as complicated typing as we'll get this year. Yeah. To go with mass number. Yeah. And look, I'll give you a better reason. Look up. In this question here, if there was friction, I would have called this friction force number 1 to go with mass number 1, friction force number 2 to go with mass number 2, friction force number 3 to go with mass number. Just so that when I write FF, which one was I talking about? Easily get a little bit organized and you don't have to worry about it. Is that all right? Built-in error check, I know it's going to be less than 9.8. I have no idea what the answer is here. 8 times 9.8 minus mu times 9 times 9.8. Don't close your bracket, Mr. Dewick. Minus 1 times 9.8. I probably didn't need to type the 1 times. Divided by bracket 1 plus 9 plus 8. You'll get 2.586 and then the 1 repeats? Okay. So I'll write, how many tensions am I going to find? I'm going to use this twice. So I'm actually going to write 2.5861. I'm going to go like this, 2.5861 repeating. And then I'm going to go 2.59 as my final answer. But that way, if I need more sig figs to get a more accurate answer later on, and I've accidentally cleared my answer button, I'm okay. Okay, don't clear your calculator. Let's find tension 1 first. Which mass would I not want to use to find tensions? Which mass looks so cluttered because it's got a bunch of forces on it? Which one am I going to avoid? Yeah, I'm not going to use 2. I'm going to use mass 1 to find tension 1. I'm going to use mass 3 to find tension 2. I'm going to avoid, you could, but why? So I'm going to put a little part B like this, and I'm going to draw a line in the middle of the page. I'll find tension 1 on the left. I'll find tension 2 on the right. Look at mass 1. What's my equation? T1, because mass 1 is accelerating which way? Upwards. So winner must be upwards. So T1 is a winner. Minus M1G equals M1A. How would I get the T1 by itself? T1 equals M1A plus M1G. Here I can use my answer button because I still have the 2.5861 repeating stored. What was M1? I've scrolled down.
M1's 1.
So it's going to be 1 times answer button plus 1 times 9.8. You get 12.4?
No.
Yes?
Yeah, that's
Oh, I'll put a box around that because I'm kind of proud. 1 times 2.59 plus 1 times 9 point, or 1 times answer button plus 1 times answer button. Okay. Yeah. Yeah, some of your calculators, you can go back several lines, and this is where I've gone on my rant about you should have a good calculator and figure out how to use it. I've taught you some of the basics, but most of you have some neat features in your manuals that you don't even realize. What's the equation for the right-hand mass?
Wait, so it's 1 times, what's the first?
Answer button, ANS.
Right. 1 times ANS plus 1 times 9.8.
M1A plus M1G, where A is that, and it's stored on my calculator. Yeah, the answer button won't work if you have the wrong answer in there. So you might have to go 1 times 2.5861 plus 1 times.
I got the right answer. I guess.
Okay. What's my equation for mass 3?
M3G minus 2.
Oh, because there, gravity's winning on that side. We're accelerating down.
Yeah.
So M3G minus tension 2 equals M3A. Swappy dance.
Switch the T2 with the M3A.
Folks, you've come such a long way. I'm so proud. This is so much nicer to teach it this way than plugging in numbers and getting stuff by, oh. So I think we're going to get tension 2 equals M3G minus M3A. How big was M3? I've forgotten.
M3 is 8.
So it's going to be 8 times 9.8 minus 8 times 2.5861. That's 5 sig figs. That should give me at least 3 sig figs of accuracy in my answer, because I can't use my answer button anymore.
5.77.
Yeah, you could do that as well. Fill a bunch of ones in like I just did. And I get 57.7. Okay.
7.9.
What did you use for A? What did you type in for your acceleration?
2.5861.
You should have got 57.7.
Oh, no, I'm stupid.
Yeah.
Okay. What's your homework?
We don't have homework. And the quiz.
Take home quiz. Number 1 and number 2 are the same question, different numbers. So I'm going to say do number 1. If you get it right, great. Skip 2. If you need more practice, you can try 2. 3 is good with friction. 4 I'm going to cross out. It's 3 masses with no friction. I'm going to make you do the tougher one with friction, because if you can get that, then you can handle the one without friction, so we won't even bother practicing it. 5 is good. No. 5, too easy. No friction. I'm going to give you friction on the test. I like number 6. I like number 6. That's what you're going to get on the test. A hanging mass, and the other mass has some friction underneath it.
Number 6 on the
Okay.
test, everyone.
I'm going to put a star next to number 7. This is tougher than I would ask. Number 7 asks this. A, find the acceleration of the system. That's fair game. Look up. Pretend this is a 14 kilogram mass. That's the trick to doing A. But then B says, find the coefficient of friction on the 2 kilogram mass. That I'll let you see if you can figure out. If not, I'll answer that on Monday. So that's the tricky part, part B. Okay? 8 is good.
Great.
Ooh,
That's it.
what's number 9 asking me to find?
If the system below remains at rest.
So first of all, if it's at rest, what's the acceleration exactly as a number? Okay, that works. What's it wanting you to find? So it's very, very, very similar to this hanging mass example, but you know what you're going to get by itself? The mu. I'll let you see if you can figure that out. I haven't done one like that. If not, I'll talk about it. Well, we've got the mu by itself, but not this challenging. So 9 is okay. I would consider 9 and A minus A level questions. So if you find it tough, you're normal. Number 10 is the same as number 9, but even tougher because A isn't 0.
12 is so nasty because we skipped 11. That's not bad.
Number 12, you can put a star next to.
So,
I'm not going to ask you one this tough. This is actually from an old Physics 12 scholarship challenge, but I'm going to tell you, if you think about this right, it can all be solved with clever Physics 11. Okay?
Just be clever though.
So let me emphasize, 12, if you can't get it, don't freak out. 10 and 9, those are the upper level of what I'd expect you to handle, but I would definitely expect you to handle something like number 6. And I would definitely expect you to handle something like number 3. Okay? And the take-home quiz. So you got about an hour, lots of time. Use it wisely.